This tape describes our experiments with three-dimensional motion planning using the infrared sensitive skin developed in our laboratory. Shown here is the skin before the installation on the arm and before the infrared sensors, about 500 of them altogether, have been placed on it. This is the circuit board that contains the electronics for the sensitive skin. 3 such boards are used in the sensor system. As you can see, the printed circuit material is quite flexible and can be easily bent. Here is the robot arm covered by the sensitive skin. The entire body of the arm is covered, therefore objects approaching from any direction can be detected. The inter-sensor spacing is less than 2 inches, depending on the curvature of the skin. Using a CCD camera that is sensitive to infrared light, we can see the pulsing of the LEDs. The scan rate is about 17 Hz, thus the entire skin is pulled once every 17th of a second. The sensor operates at a distance of up to 7 inches and uses amplitude modulated infrared light for the detection, which increases its immunity to ambient light and allows the operation of multiple sensors. To give the viewer an idea of the time multiplexing sequence, the scan shown here is slowed down approximately 15 times. Since the sensor transmits its own light, the robot can work in a variety of lighting conditions. This was taken in a dark room using the CCD camera, and although it is difficult to see the obstacle, you can guess its location when it occasionally occludes the arm. Using the sensor data processing algorithm we developed, we can cause the arm to move away from obstacles. This capability may be important in applications where the safety of the robot body or surrounding obstacles is an issue, such as, for example, the safety of astronauts or cargo in space applications. The planning of this motion is done by finding the local normal of the obstacle in configuration space and using this to move the arm. In the case of 2 or more obstacles, the arm will move away from them if there is free space. If the arm is trapped, for example, if it is between 2 points, it may oscillate if its speed is high relative to the reaction time of the sensor. This is an example of fully automatic 3-dimensional motion planning. To show that no contact takes place, the objects in the foreground are not attached and would be toppled if they were touched by the robot arm. Shown here is the same experiment, documented on the monitoring workstation. Shown are various perspective and Cartesian projections of the arm's trajectory in the configuration space. The blinking figure on the right represents the real-time motion of the arm in its workspace. These curves help us evaluate various characteristics of the motion, such as its smoothness and the handling of the narrow gap between the 2 obstacles. These 2 arms share common space and present moving obstacles for each other. The traditional way of handling such a situation is to impose a control system which has complete information about both arms and dictates their motion at every moment. Such a structure is too computationally expensive and therefore not practical. The system here is based on a more democratic approach, in which each of the two arms goes about its own business without thinking about the other arm. When challenged, the smarter arm, with the sensitive skin on the right, simply gives way to the other arm. This is the simple master arm built for our telerobotics research. The arm's kinematics are similar to the slave arm, including its joint limits. The three potentiometers read the arm position and sends them to the motion planning system of the big slave arm. By moving the master arm in this hybrid planning system, the operator causes the corresponding motion of the slave arm. However, when the slave arm encounters obstacles on its way, it abandons the slave mode and maneuvers around the obstacle using the data from the master arm as intermediate goals rather than faithfully reproducing them. In other words, this autopilot intervenes when the task becomes too difficult for the operator. Using this system, it is easy to become reckless with the master arm. This is another example of teleoperation. An undesirable but unavoidable object appears in the workspace. As one can expect, conflicts can take place in the control scheme of the hybrid system. Here, the operator would prefer to simply eliminate the obstacle. However, the arm manipulator insists on collision avoidance. The arm manipulator wins in this case. Another example of teleoperation. Notice that the teleoperator trusts the system enough and intervenes only sporadically to change intermediate goals. This may be important in crowded environments, such as this one, where the operator cannot see the whole space because of various occlusions, or when he does not have the time to figure out a precise trajectory. Finally, an example of fully automatic operation. The operator gave the arm the target position and left the task of motion planning and collision avoidance entirely to the arm.
Okay.